Greetings everyone, my name is Ju Sung, and for this talk, I'll present BAND, a mobile inference system for handling multi-DNN workloads using mobile processors. This work was done with my colleagues and advisors at Seoul National University. Okay, so I'd first like to draw your attention to mobile applications that involve multiple deep neural networks, such as virtual reality and extended reality applications. These applications have the common requirements of having to execute multiple DNNs concurrently in real time. For instance, the person finder application shown on the left involves face detection as well as face identification to pinpoint a specific person. And also, the application could also be running other models such as object detection on the front camera of the smartphone for other purposes. We also have to consider that these applications are running on mobile devices, which are typically equipped with processors of limited resources. And recent devices come equipped with multiple such processors. For example, the Google Pixel provides Google's own edge GPU and is also equipped with GPU and DSP from Qualcomm. Now, a major problem occurs when we try to run these applications on these mobile DNN frameworks like TensorFlow Lite, MNN, and NCNN, because these frameworks mostly focus on optimizing the execution of a single DNN and do not consider coordinating the concurrent execution of multiple DNNs. Say if you wanted to run two DNNs using TensorFlow, then we would have to create two separate processes that each have its own TensorFlow runtime and then serve the two DNNs on each process. This setup prevents us from comparing the performance of the DNNs and coordinating them on the mobile device. Also, if the two DNNs happen to use the same processor, such as the GPU, then we cannot avoid processor contention. And this is especially evident in multi-application use cases, where individual app developers may designate the same processor when running their DNNs in their own apps. And also, there is also the problem of only utilizing a single processor at a time. So if you wanted to use both the GPU and NPU on a mobile device, then again, we would have to spawn two separate TensorFlow runtime instances and dedicate each runtime to each processor. So there is no coordination for multi-DNN workloads and no coordination for multiple processors when using these existing frameworks. There are also some researches that do utilize multiple processors to serve either single DNN or multi-DNN workloads, such as Layer Weaver, that concurrently runs compute-intensive operators with memory-intensive ones, or MicroLayer, that splits the channels of convolution and FCE operators across the CPU and GPU. But all of these frameworks impose some assumption on workloads or processors, limiting their applicability to general multi-DNN workloads on modern devices. And what we want is a more general framework that does not involve such assumptions. So to this end, we designed and implemented a mobile inference system called BAND. BAND utilizes the heterogeneous processors on a mobile device to serve multi-DNN workloads, coordinating DNNs and processors to achieve good performance. And as shown in the evaluation preview below, utilizing more and more processors lets BAND gradually process more frames per second for multi-DNN workloads. So for example, using only the CPU on the Pixel 4 nets us about only 3 frames per second, but adding the GPU, DSP, and NPU contributes to the FPS performance, and eventually we top at around 12 frames per second. So before delving into system details, I'd first like to cover the various challenges that we encountered while building the system: heterogeneous process contention, fallback operators, and execution time fluctuations. So the first challenge is that processors have heterogeneous processor performance characteristics. So when scheduling a DNN on a processor, we have to compare the expected inference latencies on each processor. For instance, for the Galaxy and Redmi devices, it is obviously more favorable to use the HTA and APU processors because of the differences in execution times. But note that this doesn't necessarily imply that we can simply fix the processor and DNN assignment because of the dynamic nature of workloads. So for example, if we keep assigning DNNs to the fastest processor, then that particular processor may become overloaded, and it may be more preferable to use the other slower processors. This is especially the case if the execution times of a DNN do not vary greatly per processor, as in the Pixel device. And our solution to this challenge is to maintain a central scheduling component that acts as the mastermind, and also put per processor workers that run DNNs by following orders from this central scheduler. And I'll talk more about this in later slides. The second challenge is the existence of fallback operators. So unlike server GPU environments, DNN operators in mobile environments have the tendency of not being supported by specialized processors due to both design and implementation issues. And such operators introduce new scheduling opportunities that are missed by existing frameworks. For example, TensorFlow Lite here deals with fallbacks in a silent manner. So in the timeline shown below, we are running the efficient net model, the orange one, on the NPU, and the mobile net model, blue, on the CPU. And at around 7 milliseconds, the framework discovers fallback operators in the efficient net model and falls back to the CPU to run those operators. However, this information is not propagated back to the mobile net model, and mobile net keeps running on the CPU. This could have been managed much more efficiently if we just delayed the execution of the mobile net model until the fallback in efficient net occurs. So as mobile net runs faster on the NPU than the CPU, we could have just reduced the inference latency of mobile net by utilizing this idle time of the NPU. And such a schedule is impossible in base TensorFlow because of the silent fallback mechanism. So our solution to this problem is to schedule DNNs in units of subgraphs. And by partitioning DNN graphs so that fallback operators and non-fallback operators are put in different subgraphs, we can explicitly control and manage when a processor becomes idle due to CPU fallbacks, and better utilize such idle times by scheduling other DNNs, like the timeline shown in the previous slide. I'll talk more about this in later slides. The third and final challenge is the fluctuations in DNN execution time. So it is well known that the DVFS mechanisms, the frequency mechanisms in mobile environments greatly affect the DNN inference performance. For instance, in the inference latency CDF shown below on the left, you can see that the green line spans across quite a wide spectrum. And this line was plotted by measuring inferences with idle intervals of random lengths in between each inference. And due to these idle intervals, the device constantly adjusts the processor frequencies, and as a result, the inference latency varies greatly. And in terms of scheduling, this complicates matters as it is difficult to accurately predict how long a particular DNN or subgraph will take. So Band's solution to this matter is to have various system mechanisms that reduce the unpredictability of DNN execution times, such as scheduling at most one subgraph at a time for a DNN instead of the whole model, and maintaining a dynamic latency profile for DNN execution times. So to recap, we have these three challenges and three solutions for each of these challenges. Central scheduler, subgraph partitioning and scheduling, and other various system mechanisms for dealing with execution time fluctuations. We neatly pack these solutions into our system, Band. So the previous solutions are handled from various system components. First, applications submit their DNNs they want to run, and the model analyzer component checks these DNNs and generates subgraphs. And the scheduler receives these subgraphs and dynamically determines which subgraphs to run for the DNNs. And the scheduled DNNs are run on processors via processor-specific drivers. I'll now clarify our notion of subgraphs and then explain each component in detail. So the subgraph is not an entirely new concept. In fact, we just follow the conventional definition of a subgraph. In other words, a subset of the operators, of all the operators within a DNN graph, and the edges or tensors connecting those operators are grouped as a subgraph. And so naturally, when running two subgraphs in succession, we need to pass the intermediate tensors across the subgraph boundaries. But what makes the notion of subgraphs so important for our system is that it is solely up to our system to decide how to form subgraphs and how to run them. The processor to the processor to run a subgraph is not fixed and must be determined by band and runtime. And moreover, instead of predetermining a schedule of subgraphs for a particular DNN, we generate many subgraphs and dynamically choose which ones to run at runtime, as workloads have dynamic characteristics. For instance, the subgraphs that are used to run a DNN may differ for a busy situation in which most processors are running some other DNNs, and a relatively relaxed situation in which most processors are idle. So, the model analyzer component in band is in charge of preparing these subgraphs in advance so that the scheduler can later choose which subgraphs to run at runtime from the prepared candidates of the subgraphs. And as I mentioned earlier, we partition DNN graphs so that fallback operators and non-fallback ones are separated. But generating subgraphs with fallback operators is not a trivial task, as there are multiple processors available for a mobile device, and each processor has its own set of fallback operators. And I will not go into details in this talk, but just to give you the picture regarding subgraph partitioning, our approach can be considered as the middle ground between model-level scheduling and operator-level scheduling. So model-level scheduling has the aforementioned problem of silent fallbacks, but that doesn't necessarily mean that we should just schedule DNNs at the granularity of operators, because an overly fine-grained schedule may result in excessive processor transitions. And having too many transitions incurs inter-processor communication overheads and does not allow us to enqueue many kernels into a processor at once. So the overall execution time may not improve as expected. So instead, we take the middle path and work with scheduling units of subgraphs that are fine-grained enough to avoid silent fallbacks, but are not too fine-grained so that frequent processor transitions is not a significant issue. So instead of directly generating subgraphs from DNN operators, we first group adjacent operators into units and then create subgraphs from those units. And these units serve as the stoppers for overly fine-grained schedules. Please check our paper for more details. Oh, okay. Next, the scheduler. The scheduler receives the, oh, sorry, I'm on the wrong slide. Okay, so next, the scheduler. The scheduler receives the generated subgraphs from the model analyzer and dynamically chooses which subgraphs to run. And in order to devise an accurate schedule, the scheduler consults execution time profiles for subgraphs, as well as whether processors are currently running other DNNs. We provide a pluggable scheduling policy interface to match the diverse requirements of mobile applications and support basic policies such as least slack time. For instance, for the DNN shown below, the upper subgraph sequence is expected to finish earlier than the one on the bottom. So the upper one is chosen, and the scheduler schedules subgraph A and B. And keep in mind that as we want to be able to react to unexpected fluctuations in latency times, we do not schedule the subgraph C ahead of time. We rather reconsider C's processor placement only after subgraph AB has finished. Regarding execution time profiles, we continuously update the expected latency of a subgraph at runtime. So after predicting the execution time of a subgraph when it is first generated based on operator flops, we continuously update the latency based on the actual measured latency of each subgraph when those subgraphs are scheduled and run at runtime. Before moving on to our evaluation, I'd like to mention one more important aspect regarding thermal throttling. So as we try to utilize all of these processors, a processor may get shut down due to thermal throttling. And we've confirmed that for an intensive multi-DNN workload, band does not experience any thermal issues for about up to 10 minutes. But in the long run, however, a processor may actually get shut down. And if such an unfortunate case occurs, the corresponding worker for that processor is disabled and excluded from scheduling. So, and the subgraph that was running on that disabled worker is put back into the scheduler. And band continuously pulls the disabled processor until it becomes online again. Okay, so I'll now show you our key evaluation results. We use devices from Google, Xiaomi, and Samsung for our experiments. And we compare our system band with the TensorFlow-like baseline, as well as a slightly optimized version of TensorFlow called TF-like plus MP. And we use several multi-DNN workloads. For instance, the eagle-eye workflow is a person identification workflow that is shaped as follows. And multiple DNNs are connected with these intricate dependencies. And a single image frame from eagle-eye is regarded as finished when all DNNs for each image patch in the input image has finished running. And likewise, DiceStream is a live video analytics workflow that also consists of DNNs of various tasks. Okay, so the following figures show the frames per second for each workload, device, and framework. Our framework band, which is shown in blue, is constantly performing better than the red TF-Lite baseline, as well as the green TF-Lite MP baseline. And the best case is in the Xiaomi device for the eagle-eye workload, where band performs 5 times faster than baseline TF-Lite. And you can also see that the subgraph partitioning and scheduling mechanisms also contribute significantly from the differences between band and band with no subgraphs, shown in yellow. And note that the contribution of these subgraphs differs per workload and device. And for instance, utilizing subgraphs yields larger performance improvements for the DiceStream workflow than the eagle-eye workflow. And this is because the DiceStream workflow involves more concurrent inferences than eagle-eye. So our system can come up with more intertwined schedules that efficiently utilizes the processors on the device. And next, this timeline shows a specific scheduling instance for eagle-eye in the Pixel 4 phone. In model-level scheduling, the FSRNet model, shown in yellow, it seems to occupy the DSP and NPU for a very long time. However, it turns out that the CPU fallbacks were occurring all over the place. And so in the subgraph level scheduling timeline shown below, the CPU fallbacks are explicitly managed and the processor idle times are utilized by other models, other DNNs. Okay, so finally, we have a very short demo video that showcases band's performance. So both band and baseline TensorFlow are processing a live video stream with face detection and identification models. And the screens are being updated after the framework's finished processing a single frame. And as you can see in the upper half, our system is able to process frames much faster than baseline TensorFlow, resulting in a smoother screen. Okay, so to summarize, we built a mobile inference system called Band that utilizes the various processors on a mobile device to serve multi-DNN workloads. And we incorporate various techniques such as subgraph mechanisms to achieve up to 5 times throughput compared to baseline TensorFlow. And that is the end of my talk, and I'll happily take any questions. Thank you.